Other measurements commonly used in statistics are measures of dispersion, shape, and association. See, while a central location, like the average, is a good measurement of what is the middle of your data set that you're working with, what happened normally, typically on average, it doesn't capture how much variation, how much difference there is within the individual returns that you had in that sample. So a measure of dispersion helps to gauge the variability of the variable that you are testing for. For example, if we're talking about the median income of an area, if everybody is very tight around that average, then you're going to have a very low measure of dispersion. Whereas if you are taking the median income of an area that has a lot of people that don't make very much money at all, and some people that make a ton of money in there, you're going to have a lot more variance. This measure of dispersion will capture that when you're expressing that information and you're using it to make good decisions. A measure of shape, very similar to a measure of dispersion, except it figures out what is the typical distribution around that central point. Is there about an equal amount below it and above it? Well, then you're going to have symmetric distribution. Are you going to have very few points above it, a lot of points below it, but those points that are above your average are way, way above the average? Well, then you'll have a very skewed to the north or skewed above distribution as well. So a measure of shape shows how all of the points in your set relate to that average. And then lastly, some things tend to cause other things to change, and that is a measure of association. With those two variables, is there a relationship between the two? Going back to median income in an area as well, or mean income in an area, they say that a college education is the greatest thing you can do to increase your lifetime earnings. So if you were sampling people about how much they make, you would at the same time sample them how many years of college they created, both quantitative variables, and now you could use some measure of association to figure out if this is indeed true. So for measures of dispersion, the simplest measure that you can have is the range. It is simply the highest point and the lowest point in the set, finding the difference. So if you're taking a test, it's the highest grade in the class minus the lowest grade in the class, and it gives you the overall range of the results that you got. The problem with the overall range like that, the full range, is that any one outlier will definitely cause that to be a huge number. One extreme observation in your sample set will cause it to have a huge range. And while all the other ones might be tight around that median, you're still going to have a very, very big range due to one wild number. So statisticians, if I could talk, would more normally use the interquartile range, or the IQR. The formula for that is the third quartile, which is the 75th percentile of the data, minus the first quartile, the 25th percentile of the data. So what you're doing is you're finding the point that has 75% of the information below it, the other point that has 25% of the information below it, and by finding the difference between those two, you're observing the middle 50% of the returns that you had. And that way you get a good measure of how far away from that central location your data spreads, without it being so distorted by your outliers, your extreme observations. The mean absolute difference, or the MAD, if you will, is just what it sounds like. It's the arithmetic mean of all of the differences of each data point has from your average. So if you're doing it for a population, you would find whatever the return was for a particular data point, how far away that is from the average, and you would keep doing that for every point that's in your data, adding up all of the differences that you have, and when you find the sum of all those differences, you divide it by n, the size of your sample, and it gives you the mean absolute difference, the average difference, if you will, of any one given point in your information. For a sample, it's the same exact process, but again, now we're not going to call the average mu, we're going to call it x bar. The problem with the mean absolute difference, while it is useful, is that it's not standardized. If you are measuring something that is measured in very high numbers, you're just by nature going to have a very, very high MAD. If you're a production company that's making two different pieces of inventory and one takes, say, on average 20 minutes to make, because it's not that complex, then you have another very complex piece of inventory that you're making that takes 200 minutes on average, guarantee that second piece of inventory that takes 200 minutes on average to make is going to end up with a higher mean absolute difference, just because it's going to, all of the returns you have are going to be measured in such a higher typical number. It's not going to be standardized. People will typically use the variance, or even more importantly, the standard deviation, to measure something in this case. And it's very similar to what you had with the med back over here, as we can see on the slide. It's pretty close to the same formula. Only difference is this little guy right here, square. Well, what happens when you square something? 2 squared is 4, 4 squared is 16, 6 squared is 36, 9 squared is 81. A small change in the difference, so you have a slightly higher number. When you square it, becomes a much bigger number, much faster. It grows exponentially. So by doing this, what you're basically doing is putting more emphasis on the points in your information set that are farther away from the average. And it's incredibly useful for points when you're working on stuff where having even one number that's incredibly far away from the measure of central location could be very bad for whatever you're doing. If you're testing how much a certain medication might increase somebody's heart rate, well, one very high number, and there's not something you want to have, because it's probably not going to be good for the health of that person. If you are working on an assembly line, making parts that have to go from one phase of production to the next, if you have a spot in there in your data sets where how long it took you to get through each phase every single day, you have one number that's way higher than everything else. Well, you know what that did? That log jammed and backed up production, which hurt the whole overall profitability of your company. So variance is more commonly used because it puts extra emphasis on those outside points that you have very far away. That being said, when it's represented, people will typically take instead the standard deviation. And all that is find your variance using one of these formulas up here. And then after you found it, take its square root. And it's useful in this case because, well, first, just from a representative point, if you have a lot of variance in there, anything that's far away, and you square it, you might have a really high number for variance, but taking the square root of it kind of brings it back down to earth. And it also is going to give you a number in your return that's much easier to work with later, to comprehend, to use for information, because it's going to be relative in this case to the size of the sample that you have. The coefficient of variation is an even better way to find a relative measure of dispersion. Why is that? Well, all you do for this, depending on if you're working with an entire population or just a sample, is you find the standard deviation of that information and you divide it by the arithmetic mean of it, the average. And what you're doing in that is you're saying, okay, the average return of variance that we have in here is equal to this percent of the average that we have. So if you are making a good that takes 20 minutes to make, and your standard deviation is 2 minutes, in that case, what you're saying is basically the amount of variance that we have in that is equal to 10% of the actual time it would take to make something. And now you have a much more useful number to work with, because you know what kind of expectations you can have, and you can compare project to project, item to item, because percentages are the same no matter what size number you're measuring in. To put this into something that's commonly used in the business world, you'll have the Sharpe ratio in this case. And the Sharpe ratio follows the thoughts that all investors have, is the more risk I'm taking, there better be a better potential for return. So what you would do is you would go and find your return as a data point. We're going to have that be our xi, and then for a period of time it would be our arithmetic mean of all the different returns we had, and figure out how that compares to the risk-free rate. What is the risk-free rate in investing? It is the amount of return you could get on something that there is zero risk in, and it's commonly used as the Treasury bill. U.S. government has never defaulted on any loans that they've taken out from the public. I doubt that they ever will. There is really no risk in investing in bonds and bills from the U.S. government. So they typically use that as the risk-free rate. So basically the numerator in this little formula we have over here is how much the average return for any one particular investment over a period of time has exceeded what you would have made if you invested in the Treasury bill and took that risk-free rate. And then underneath you have the measure of dispersion, the standard deviation for that same sample set. What would a standard deviation be for investing? It'd be the variance in the return that you had. Did you lose a lot of money? Did you make a lot of money in any one given period? And now you're comparing the return that you got above the risk-free rate to the amount of variance there was from period to period in the returns. And now, with this ratio, with this number that returns, you get a better idea of how well you will be compensated for a particular investment compared to the risk that you are undertaking for that investment. And you can look at a bunch of potential different investments you had and which one is going to give me the greatest amount of return, hopefully, compared to the amount of risk I'm willing to take.